In the previous sessions, we had discussed about cyclic groups, the properties of cyclic groups and everything. So in this session, we'll be considering some common examples of cyclic groups. Okay, so before that, what's a cyclic group? A group G is said to be cyclic if there exists an element A with the property that every element of G can be written as a power of A, where R is element of Z. So we denote another symbol. So we denote G as a group being generated by A. So this is the symbol. The symbol means this entire group is being generated by A. Okay, so what are some common examples of cyclic groups? One very famous example is a set of integers under addition. Okay, you can see that all the integers are being generated by 1. Okay, because 3 can be written as 1 plus 1 plus 1. This is actually it is 1 cube. Okay, so here 1 cube, don't confuse it with multiplication. Here the operation is actually addition. Okay, and similarly minus 3 can be written as minus 1 plus minus 1 plus minus 1. This is actually minus 1 cube, and minus 1 is actually the inverse of 1, so this is 1 raised to minus 3. Okay, similarly you can see that minus 1 also generates z, so there can be many generators in a group. In this group there are basically two generators, 1 and minus 1. So we have discussed now an example of infinite cyclic group. Okay, similarly let us look at finite cyclic groups. Okay, so similar analogous to Zn, the set of reminders which we are obtained when you divide a number by n. So Zn under the operation addition modulo n is also a group. Okay, for example, so in this Zn consists of 1 will be there, 2, 0 will be there, 1 will be there, 2 will be there, etc. up to n minus 1 will be there. So this is actually Zn, and here you can see that, for example, if you take Z6, it consists of 0, 1, 2, 3, 4, 5. Okay, so this is also a cyclic group because you can see that all the elements are being generated by 1. Okay, how? Because 1 is obviously there, and 2 is actually 1 plus 1. Here the operations addition modulo 6. 3 is actually 1 plus 1 plus 1. 4 is actually, again if you think, 1 plus 1 plus 1 plus 1, and 5 is actually you have to take 5 ones, and 6, if you take 6 ones you will get again remainder 0. So 2 is actually 1 square, 3 is actually 1 cube, 4 is actually 1 raised to 4, 5 is actually 1 raised to 5, and 0 is actually 1 raised to 6, and goes on. So if you take 1 raised to 7, again you will obtain 1 and 1. Okay, because we are considering only the remainders, we will divide by 6. Okay, so there are also other generators. You can also check that 5 is a generator, because if you take 5 raised to 1 you will get it as 5. 5 square would be basically 5 plus 5. Okay, 5 plus 5, that is 10. So in this group that will be our 4. If you take 5 cube, it is 15. So in this group that would be 3. If you take 5 raised to 4, that will be 20. In this group it will be 2. If you take 5 raised to 5, it will be 25. In this group it will be 1. And if you take 5 raised to 6, that would be 30. In this group it will be 0. So you have obtained every element. So you can also check whether there are other elements also. Okay, so we have discussed some common examples of groups. One is the infinite cyclic group, that is Z under addition, and also Zn under addition modulo n. Okay, now we are going to derive an important result. So before that, let us also discuss some other type of cyclic groups. So here I am going to discuss one new group called a group of units denoted by un, the symbol un, under addition multiplication model, under multiplication model n. So what is un? Okay, so basically if you take u9, okay, u9 consists of those numbers which have no common factors with 9 except 1. Okay, so those which are relatively prime to 9. For example, this group will have 1 would be there, 2 would be there, 3 will not be there because 3 and 9 have common factors apart from 1, which is again 3. Again 4 will be there, 5 will be there, 6 will not be there because 6 and 9 has common factors, 7 is there, 8 is there. Okay, so this is the group u9. Okay, so similarly what will be u10? Okay, u10 you will have using the same concept, those factors, those numbers which do not have those numbers which are less than 10, which are positive and which do not have common factors with this 10. Okay, so except 1. Okay, 1 is there, 2 will not be there because 2 and 10 has common factors, 3 will be there, 4 will not be there, 5 will not be there, 6 will not be there, 7 will be there, okay, 8 will not be there, 9 would be there. Only 4 elements are there in u10. So I hope you understand what is u9 and u10, and here the operation would be multiplication modulo 10, because if you take 3 into 7 you will get it as 21. In this group it is actually 1. Okay, similarly 7 into 9 is 63. In this group it is actually 3. You can check whether un is a group under the various operations. Okay, so here we claim that basically this is a cyclic group. Okay, so if you consider this u in ion, okay, So let us look what. So there are many generators are there. In particular, suppose if you take 2, okay, what is 2 in 2 square? 2 square is actually 2 into 2. You will be getting 4. What is 2 cube here? It is multiplicative modulo n. So it is 2 into 2 into 2, which is again 8. That is also there. What is 2 raised to 4? We will get as 16. In this group, 16 is actually under multiplication modulo 9. 16 is actually 7. Okay, 2 raised to 5 is actually 32. Okay, so in this group it is actually, what is it, under multiplication modulo 9 it will be actually 5. Okay, 2 raised to 6 is again 64. In this group it is actually 1. Okay, I think we have worked in everyone. 1 2 3 4 5. Okay, so 2 raised to 1 is also there. If you take 2 raised to 0 also, you can take 1. Okay, so this so there are also other generators. So basically, if I can write in many ways I can write. So if I can write u9 is actually generated by 2. Okay, and every element of u9 can be written as in the form 2 raised to some m, where m varies from 0 less than or equal to m less than, so up to how much n, less than or equal to less than or equal to less than 6. Okay, or 0 less than or equal to m less than or equal to 5. Okay, so I have taken 1 as 2 raised to 0, not as 2 raised to 6, because both are the same things. I have used this for a particular purpose. So I have taken 1 as 2 raised to 0 and another as 2 raised to 6. Okay, so you can write either. I can write 2 raised to m is equal to, so 2 raised to m, where m varies from 1 less than or equal to m less than or equal to, so this way also I can write, but still I am using this notation to bring a important result here. So we will consider u9. This is being generated by, what you say, 2, and the powers of 2 varies from 0. If you vary the powers of 2 from 0 to 6, you don't need to take 6, because again you will be getting 2 raised to 6, we will be getting again plus 1. So you will be varying only from 0 to 5. Okay, so u9 is a group which is being generated by the powers of 2. Okay, now already you know that u9 has 6 elements. What are the elements here? 1 is there, 2 is 1 is there, 2 is there, 4 is there, 5 is there, 7 is there. Okay, 1 2 1 is there, 2 is there, 3 is not there, 4 is there, 5 is there, 6 is there, 7 is there, 8 is there. So this many elements are there in u9. So we also know a cyclic group which has 6 elements, that is our Z6. Okay, under addition modulo n. Okay, now we are trying to bring a homomorphism between this u9 and this Z6. So what are the elements of Z6? It is basically 0, 1, 2, 3, 4, 5. Okay, so how will you bring it? So it's very simple. So I am going to bring a homomorphism between u9 and Z6. Okay, now we know that every element of u9 can be written as 2 raised to m, where m varies from 0 less than or equal to m less than or equal to 5. Okay, so this was taken this was taken purposefully to bring a homomorphism between u9 and Z6. So how will you bring it? So this is, if you take an element, it is of the form f of 2 raised to m. I'll simply define this as simply m. This is where m is in between 0 less than or equal to m less than or equal to 5. So this is how we are going to define the function. Okay, let us check whether this is a homomorphism. Okay, so what is basically a homomorphism? That is f of a1 star a2 will be equal to f of a1 delta f of the operation is there. So this is the operation in the first set, this is the operation in the second set. So if you take f of 2 elements, so in this element if you take f of a into b in u9, that is actually f of 2 raised to some m into 2 raised to n there, where the operations addition modulo n and multiplication modulo n, which is nothing but f of 2 raised to m plus n, and you will get this as m plus n, that is nothing but f of 2 raised to m plus f of 2 raised to n. So you can see that the operations are being preserved here. Okay, so that is actually this is actually, this function is actually a homomorphism from u9 to Z6. Okay, so very simple homomorphism. You just take every element as 2 raised to m and you define m as simply you define the function as f of 2 raised to m as simply m. Okay, so this is basically a homomorphism, and also you can also see that this is also an isomorphism. Okay, so why is it called an isomorphism? Because it will be both 1 1 and onto. Onto is very easy to prove if you take an m element of Zn as Z6 here, and if you define if you take an m element of Z6, you should obtain an element A such that f of A is equal to m. So you just define A as 2 raised to m. So if you take f of 2 raised to m, you will be getting m by definition. That's one case. So it's onto. Okay. So when you take for onto function, if you take an element of the second, if you take an element of the second, if you take an element of the second set, you should always get a pre-image. So if you take an m element of Z6, I can take an A as simply is 2 raised to m. So when we take f of 2 raised to m, we will get it as m only. So it is basically a onto function. Now how will you prove 1 function? How we will do it? Prove it's a 1 Okay. So for 1 I'll suppose that f of A is equal to f of B. So this means actually f of some 2 raised to m is equal to f of 2 raised to n, because every element of U9 can be written in the form 2 raised to m. So I'll assume that this is true. Okay, so what is this? The meaning of this is simply m is equal to n in Z6. So it will be some. So when you consider Z6, it will be basically any of one of the numbers 0, 1, 2, etc. 5. Okay, so when you get m is equal to n, that means simply 2 raised to m will be equal to 2 raised to n. That is our A is equal to B. So once you have obtained f of A is equal to f of B, now you have shown that this means that simply A is equal to B. That means two elements can have the same images only if they are the same. That means the function is 1, 1. Two elements will have the same images only if they are the same. That means the function is basically 1, 1. Okay, so this is in fact an isomorphism. So you have found that U9 is isomorphic to Z6. Okay, so this is not a coincidence. So if you consider any cyclic group, you will have an analogous result. So if you have an infinite cyclic group, it will be actually be isomorphic to Z. Okay, and if you have a finite cyclic group of order n containing n elements, it will be isomorphic to Zn. So it's a very important result. Next we are going to discuss this. Okay, so so the first result is that suppose G be an infinite cyclic group, then G is isomorphic to Z. Okay, so how will you prove it? It's very simple. So if you consider G, it is cyclic, so it will be generated by some A. So that means every element of G can be written as some power of A, where R is element of Z. So you just define f from G to Z as f of A raised to R is simply as R. Okay, so this will be a homomorphism. So very simple. How will you do it? So if you consider two elements, so what's a homomorphism? Once again, you should have f of A dot B should be equal to f of A into f of B, where the operations are. So here this is the operation in the first set, this is the operation in the second set. Okay, it's not a usual multiplication. So in this case, if you consider two elements f of some A raised to R dot some A raised to S. This is actually, every element can be pronounced like this because it is cyclic. So this is actually f of A raised to R plus S. This is nothing but R plus S, which is f of A raised to R plus f of A raised to S in Z. So we have got the structure preserving condition here. This is basically the meaning of homomorphism. Therefore, this is a homomorphism. Now, as before, we'll prove that this is also an isomorphism. Ontoness is very easy to prove. If you have ontoness means if you are taking an element in Z, this is your G. If you are taking an element in Z, you have to show that it has a pre-image. So very simple. If you take an R, you just take my A as, you just take my G as A raised to R. Okay, so f of A raised to R you will be getting as R. So this is also, if you have taken R, corresponding you can take an A raised to R. So if you take f of A raised to R, you will be getting R. That means each and every element in Z has a pre-image. So this is an onto function. And similarly, 1, 1 function also, it is using the same idea which we had discussed earlier. So you consider two elements, maybe since I have already used A here, suppose f of P is equal to f of Q. So since this is cyclic, I can write this as f of A raised to R is equal to f of A raised to S, some form of R comma S. So this means actually R is equal to S. So what does that mean? That means like you have A raised to R will be equal to A raised to S, that is P is equal to Q. So we have taken two elements which has the same image. Now we have shown that those two elements are just the same. So this is an onto function. Therefore, we get that an infinite cyclic group is actually structurally isomorphic to our Z, group of Z under addition. So that means every infinite cyclic group can be actually be considered as our group of integers because both are just similar. So similar, if you take a finite cyclic group, suppose you are taking a finite cyclic group which has n elements. So G is a finite cyclic group with n elements. Okay, so that means G can be written as powers of a raised to r, and also I can write this r varies from 0 etc. Just like the usual example, at r varies from 0 up to n minus 1. Okay, so because this is finite, so all these powers will be different, and also just like the previous example, you can consider this from 0 up to n minus 1. All these powers need to be different. You can just check it why it should need to be different. If what will happen if some powers are same, that means the order will be less than n. Okay, you just try to think why it is so. So every element can be written in the term of a raised to r, where r varies from 0 to n minus 1. Okay, so now if I consider Zn also has 0, 1 to up to n minus 1. Here operation is addition modulo n. So just as before, I am going to define a homomorphism from G to Zn by defining f of a raised to r is equal to r, where r varies from 0 less than or equal to r less than or equal to n minus 1. Okay, so as before, you can prove this a homomorphism. How? Because if you take f of a raised to r into a raised to s, this is actually a raised to r plus s, this is actually r plus s, this is actually addition modulo n here. Now r is f of a raised to r plus f of a raised to s. So the operation here is addition modulo n. So this is a structure preserving map or a homomorphism. Again, onto function, how will you prove it? So you take some s here. So how will you define? You take here it as a raised to s. So basically, if you take an s in Zn, if you take a raised to s in G, you will have f of a raised to s is equal to simply s. This means this function is onto. Okay, again one more thing is remaining. What is it? Again you have to show the one function. So using same result, you assume that f of a raised to r is equal to f of a raised to s. This means this means r is equal to s. That means actually a raised to r is equal to a raised to s. So this is also 1 So this is also an isomorphism. So G is actually isomorphic to Zn. That means every finite cyclic group of order n is actually isomorphic to Zn. So whenever you are discussing about cyclic groups, you need not look at all the examples, because all the cyclic groups are either isomorphic to Zn or Z. So this is an important result. Every cyclic group, if it is finite, it will be isomorphic to Zn under addition modulo n, or if it is infinite, it will be isomorphic to Z under addition. Okay, so thank you. Stay safe.